Hello viewers, today we start lecture number 3rd on eccentric connection. In previous lectures, we have learned about the eccentric connection when eccentric loading in the plane of bolts. But in this lecture, we will read the second type of connections, that is design of bearing bolt subjected to eccentric loading causing movement in the plane perpendicular to the plane of groups of bolts. This type of connection is shown in figure first. Figure second is similar to figure first, but more bold shown in figure second to easily explain the topic. Let P be the factor load at an eccentricity E, then the section is subjected to direct shear force which is equals to P and moment M equals to P into eccentricity. If there are n number of bolts in connection, direct design shear force on each bolt is given by VSB equals to P upon N. There is two vertical rows for bolts. These are two vertical rows and elevation is shown in as per figure first B. Now the movement causes tension in top side and compression in the bottom side. This movement P into E causes tension is upper side and compression is lower side. On tension side, only bolt resists the load, but on compression side, entire contact zone between the columns and the connecting angles resists the load. Hence, the neutral axis will be much below in these conditions. Generally, it is assumed to lie at a height of 7 times of the depth of bracket measured from the bottom edge of the angle. So this is bottom edge of the angle and neutral axis lie at a height of h by 7 above bottom edge of angle. This is our neutral axis. This is our neutral axis. The tensile force in a bolt is proportional to its distance y from the line of rotation, that means neutral axis. TBI tensile force in bolt is proportional to yi, that where TBI equals to k into y, where k is constant. Total moment of resistance m dash provided by bolts in tension is given as m dash equals to summation of TBI into yi square. Hence, TBI is m dash into y upon summation of yi square. Total tensile force in bolts is T equals to summation of TBI. For equilibrium, total tensile force equals to total compressive force. From this, we have to calculate total movement. Total movement is equals to movement carried by tensile zone plus movement carried by the compressive zone. From this equation, we have to calculate the moment calculated by the tensile zone, and then we have to calculate the tensile force TB in extreme bolt, and after that we have to apply the formula for checking this design requirement. So Therefore, we take one numeric. Design a suitable bolted section of a ISHT 75 section attached to the flange of a ISHB 300 at 577 Newton per meter to carry a vertical load of 600 kilonewton at an eccentricity of 60 millimeter. Use M24 bolts of grade 4.6. First, diameter of bolts as given 24 millimeter. Diameter of hole is 27 millimeter. Since the grade of bolt is 4.6, hence ultimate stress of bolt is 400 Newton per mm square and yield stress of bolt is 240 Newton per mm square. As per code, end distance is minimum end distance should be provided as 1.5 into hole diameter, that is 40.5 millimeter. Hence we provide in that case the end distance equals to 50 millimeter. And as per the coded provision, minimum pitch equals to 2.5 into nominal diameter, that comes out to be 60 mm. Here we provide pitch equals to 70 millimeter. From steel table or structural steel handbook, thickness of ISHT 75 is 9 mm and thickness of flange for ISHB 300 is equals to 10.6. Therefore, thickness of thinner member is taken as 9 millimeter. First of all, we calculate the bolt strength in shear and bearing from the given data. Design strength of bolt in single shear. VDSB equals to 400 upon root 3, 1 upon gamma MB. Gamma MB is 1.25. NN is 1 and ANB is 0.78 into pi by 4 into 24 square. There is one shear plane and we assuming that shear plane intercepting at thread portion of the bolt. So design strength of bolt in single shear is comes out to be 65192 Newton. Then we have to calculate design strength of bolt is in bearing against 9 mm thick web of T section because the thinner member is ISHT 75 and its thickness is 9 millimeter. Bearing strength is calculated as VDPB equals to 2.5 kb dt into Fu upon gamma MB. Firstly, we have to calculate the value of kb to determine the strength of bolt and bearing. Kb is E upon 3d naught, comes out to be 0.617. In second case, kb is 0.614. Take the smaller value of these four. So kb is taken as 0.614. Therefore, VTB is 108751 Newton. Hence, design strength of bolt is taken as smaller of these two, which there is that is 65192 Newton. Now we calculate design tension capacity of bolt as given in clause 10.3.5 of IS 800/2007, that is DTB equals to 0.9 FUB into AN upon gamma MB, that is comes out to be 101624 Newton. This TDB is less than FIB into ASB upon gamma M naught, that is 98703 Newton. Hence, TDB is taken as 98703 Newton. Using two rows of bolting, as shown in figure first. Using two rows of bolting, approximate number of bolts required in each row is calculated by the formula N equals to under root 6m upon 2v into P, and that is comes out to be 6 bolts in each row. There is 6 bolts in each row. The H equals to, now we calculate the distance H, and distance is 50. Then pitch we have to consider is as 70 mm. This pitch is 70 mm. So the distance H is calculated as 400 millimeter. 5 times 70, 1, 2, 3, 4 and 5. 5 into 70, 350, and then 50, this is end distance. So the H is comes out to be 400 millimeter. Now you have to calculate distance of second bolt from NA and distance of third bolt from NA. NA lies at H by 7. Hence NA lies with edge between first and second bolt. The distance of bolts from the neutral axis is shown in table below. We have to calculate distance of second, third, fourth, fifth and sixth bolt from the NA, that is shown in table. Since there are 2 rows of bolts, hence we have now we calculate summation of yi, which is 2029 millimeter, and summation of yi square, that is comes out to be 509684.1 millimeter square. Total movement registered by the bolt in tension M dash is M upon 1 plus 2h upon 21 into multiplied by summation of yi upon summation of yi square, that is 31.2594 into 10 raised to power 6 Newton mm. Tensile force carried by the extreme bolt due to bending moment tensile force in extreme bolt is calculated as TB equals to the total moment carried by tension bolts multiplied by yi, that is distance of extreme bolt from the neutral axis, and upon summation of yi square. The design shear force VSB is comes out, then VSB is 600 into 10 raised to power 3 upon 12. 12 is the total number of bolts. Each bolt carried direct shear force equals to 50,000 Newton. Then we have to apply interaction formula for checking that. This is comes out to be 0.633, which is less than 1.0, hence the bolts are safe. And you may perform this exercise, and in next lecture we have take validate connections.